guys, thanks for coming to Notes with me. This is a rapid review on collisions. So it's all about impulse and momentum. All right, let's start with Newton's second law. Net force is the product of mass and acceleration. And that acceleration is change in velocity over change in time, so that we can derive the relationship between these four variables. Move them around and voila, we've got impulse, and we call this side momentum. Okay, and this is all because of Newton's third law. We've got F1 is equal and opposite to F2. In this case, momentum is transferred. In a collision. We also say momentum is conserved. The sum of the momenta before the collision will be equal to the sum of the momenta after the collision. We say that when an object or system of objects experiences a net force, the impulse momentum theorem, which is change in momentum is equal to impulse, can be used for predictions and calculations. Momentum is in the direction of motion and the product of an object's mass and velocity. Okay. Impulse is in the direction of the net force and is the change in an object's momentum. Which is equal to total run-on sentence, which is equal to the net force multiplied by the time of which the force acts. I've been calling it impact time and impact force to help you differentiate between like the time of a car skid or the whole system time to just the collision time. We say total momentum is conserved in all collisions, and kinetic energy is conserved only in elastic collisions, the ones where they bounce off. Right? When it gets stuck together, some of the kinetic energy is transferred in the form of heat and deformation. Here's an example. Let's look at a teacher whose weight is 900 Newton jumps vertically from rest while standing on a scale. And let's sketch a graph here. Say we've got force and time. Let's mark this line. $900 newtons, that's the weight. Oops. Yeah, there we go. And say your scale over time might read something like that. All right. So if you ever see an FT graph, that is an invitation to calculate impulse. So we're looking for area. And don't freak out if the graph looks weird. See, what we're going to do is look for triangles and boxes, and anything that's going to add to 0, we can just deal with, and it gets a lot simpler when you break it down. So we've got a horizontal line at the weight. That's always a good place to start. And then we're going to look for triangles and boxes and try to label them. Okay, so maybe this is like one section here, kind of triangle-y. Here's another, I see 2 more sections. 1, 2, 3. So I've got kind of a triangle for 1 and a triangle-ish for 2 and kind of a box or a rectangle for 3. I'm also looking to see if anything adds to 0, and I think 1 and 2, sections 1 and 2 have similar areas, so I'm going to estimate those to add to 0. And now I'm left with just section 3. And if I look at some of my data on the graph I have that's a little more detailed, I can see that, let's see, the area for 3 right here. This is about 3 seconds. And here we've got 3.5 seconds. So that's about 0.25 seconds. And looking here on this side, this probably should go up a little higher. Say this is like 1800 to the top of section 3. Well, then we've got 1800 minus 900 here at the weight line, and that's going to equal 900 newtons. So our impulse is going to be 220 newton seconds. That's the area under the curve here. Cool, right? But the more interesting question is, what's the speed leaving the scale? Right? Well, since impulse is change in momentum, and that is equal to 220 newton seconds, and VO is equal initially to 0, we can say that initial momentum is equal to 220 kilogram meter per second. Sorry on that paper there. I'll turn the page. Now I'll just come over here. You guys can write it good on yours. And momentum is mass times a change in velocity. And the teacher's mass is 90 kilograms, you know, using Newton's second law there. So then we get a speed of 2.4 meters per second off the scale. Hope you were able to make that a little neater than I was. Next up, got probably about 2 more pages. Let's go to conservation of linear momentum. For example, we have cart A1, or cart A, comma, mass of 0.5 kilogram, moves to the right. At a speed of 60 centimeters per second. We have cart B with a mass of 1 kilogram. Is at rest. The carts collide. So, when and if the only forces acting are between the objects in the system, then momentum is conserved. So that's like all collisions. Okay, so we want to define the system, and in this case it'll be our 2 carts. We want to draw it, we want to label it, and then we want to shake the equation right off the picture. And now they don't tell us if it's inelastic or elastic. Let's go for inelastic because that way we can solve for 1 final velocity instead of 2. So let's say, what is the final if inelastic? That's our question. All right, let's draw our picture. We've got cart A moving to the right. We've got cart B. And then after the collision, they're inelastic, so they stick together. And I'm going to guess that they're going a little slower, so I'll draw a smaller arrow. We have mass of 0.5 kilogram and mass of 1.0 kilogram. And so after they collide together, they have a mass of 1.5 kilogram. And initially, cart A is moving at 60 centimeter per second. Cart B is 0, and the final velocity is what we're looking for. Now we can shake the equation right off the picture. mv plus mv equals mv. I like to put an mv for each piece. And then we're looking at 0.5 times 60 plus 1 times 0 equal to 1.5 multiplied by v. Okay, we'll break that down all the way to 30, 1.5v. Divide both sides by 1.5. We have v equal to about 20 centimeter per second. It's like the most classic calculation. You won't have a lot of calculations to do, but they'll help either way. And once you do enough of these, you can start to pick up the patterns about how fast things go based on the relative masses. I mean, just look at this one, right? We've got 1/3 of the final mass, 2/3 of the final mass, 1/3 of the initial velocity. You'll get there. Alrighty. When is momentum not conserved? Can you think of any examples? When you drop a bouncy ball and it bounces back, believe it or not, momentum is not conserved there. Even if it has the same mass and velocity, because momentum is directional, it has changed. Let's write that down. Drop a bouncy ball. It bounces back. Momentum not conserved. Even if same mass and velocity, or maybe I should say speed. Yeah. Because momentum is directional. So it would be positive and then negative, or negative then positive. Either way, it's changed. And so changed. Kind of like when acceleration changes, well, kind of like when you can be accelerating around a curve at a constant speed. I don't know, that reminds me of that. Maybe they're not the same. Okay? Yeah. I mean, you could do a collision problem here, but you'd have to do it between the ball and the earth. That's a whole nother system. All right, here's some tips. Don't start a collision problem with energy. Okay, start with momentum, and if you need, you can use kinetic energy, or if it says the word elastic. Start with momentum, and if you need it, use kinetic energy, or if it says elastic, right? A common question is this collision elastic? Here's a common question. And they'll give you all the stats about the masses and the velocities and all kinds of stuff. And the answer is going to be yes, if the initial kinetic energy is equal to the final kinetic energy. Remember, if it's inelastic and it sticks together, then some of this energy is transferred into the deformation, heat, and sound. And so this will not be true if it's inelastic. So a good way to justify if something is elastic is to show that the kinetic energy before is equal to the kinetic energy after the collision. Here's an example. So we have two carts with equal masses moving toward each other with the same speed, say 30 centimeters per second. After colliding, they bounce off, regaining 30 centimeters per second speed. But now in the opposite direction. It's always a good idea to draw a picture. I mean, you'll probably use it later anyways. Helps you get started and helps your brain access the pieces it needs as you draw. So you've got two carts, A and B, going toward each other. Same mass, same speed. And afterward, two carts moving away from each other. Oops. Same mass, same speed. M, 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 V, 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 V. Is momentum conserved? The answer is yes, and you don't need to calculate anything, really. As you can see, the only forces acting on the carts are exerted by the carts themselves. So you could just claim that. Here's a question. Is momentum conserved? Yes. No calcs needed. Sometimes they tell you in a free response with they'll say something like, without doing calculations. And so if you rely only on calculations, you'll be like, aha. But yeah, is momentum conserved? The answer is yes. My justification would be something like, in a collision, momentum is always conserved because the only forces acting on the carts are exerted by the carts themselves. Just so I have more room, I don't have to squish it. Another good question is kinetic energy conserved? Or like I said, they'll say, is the collision elastic? And this is where you're headed. So, but if they say it's an inelastic collision, or if any point they stick together, it's easy. It's just a no is the answer to that. Some energy is converted to heat and sound of the deformation in the collision. Elastic? Let's see. Does the initial kinetic energy equal the final kinetic energy? Let's look. We have our picture from last time, our M's and V's for 4 pieces, but we're not going to play with momentum. So instead of dropping the momentum equation off of a picture, I'm going to drop the kinetic energy equation off the picture. So I've got A and B. Okay, and they have masses and velocities. And I'll say that 1/2 mv squared plus 1/2 mv squared is equal to 1/2 mv squared plus 1/2 mv squared. With all the appropriate initials and finals and all that good stuff. Okay, let's see. So 1/2 multiplied by 1 by 0.3 squared. And let's just multiply this by 2 because I'm adding it twice. Okay, do the same thing on the other side. I'll end up with 0.45. 0.45 equals 0.90. 0.90, yes, KE conserved. Okay, and that is just a little bit about the first conservation law, conservation of momentum. We've also shown you a little bit more about conservation of energy. I'm hoping you'll see how all the pieces from the whole year are really how we do real problems, and we do them all at the same time, or at least 2 of the 3 of them. And energy and momentum are definitely a possibility. I'm going to teach you next time, or review next time about work and energy. And then we're almost to the finish line here. So you guys have a good night, and let me know in the comments or an email if you have a question or you noticed a mistake, and I'll retape it. It's getting pretty late over here. I hope you guys are getting a lot of sleep, and I hope you get everything you need. All right. Talk to you guys soon. Bye.